Okay, folks. So, where I teach, we primarily do algebra and trigonometry-based physics classes, although we do have an AP class working with calculus. But some folks will take our classical mechanics course and have some calculus experience, or will want to refer to this once we get started with our AP electricity and magnetism class. So let's take a look at what calculus is involved in one-dimensional kinematics. So we've hinted at this before when we're looking at the relationships with graphs and the different quantities. We know that velocity is the time derivative of position. We know that acceleration is the time derivative of velocity. You may not have seen this idea in a calculus course, but I want to talk about the idea of a mathematical operator. So we talk about, when we do math, we do mathematical operations. And when we say operation, it basically means you're going to take one or more numbers and we're going to do a thing to it to get a different number result. Could be the same number, but we're going to get a number result. And you've been doing math operations as long as you've been doing math, and you've seen operator symbols as well, because addition, the operator is just this sign. Subtraction, it's just that sign. Division, commonly that sign. Multiplication could be that sign, could be that sign. Those are all operators. The radical is an operator. So all of these are things that represent, you stick them around other variables or numbers, and that means you're doing a thing to it. You're doing a math operation. So when we look at the derivative, the rate at which position changes compared to time, the rate at which velocity changes compared to time, it's like we're saying, oh, we're doing the time slope, the time change rate of x, the time change rate of velocity. The operation we're doing is find the rate at which the thing changes with time. And so we pull that aside and call that the operator. We say that this is our operator for our derivative. It's like sticking aside from the position. We're going to do that to the position. So it started off looking like you were working with fraction, working with slopes. But now I'm saying this whole thing is like, some other type of symbol, like a radical or a plus sign or a sine function or something. So that means they can nest. And so this means that if you ddt your velocity, then this is what goes on. You're taking the time derivative of the time derivative of position, the rate of change of the rate of change of position. And so the acceleration gets to equal what we call the second derivative of position with respect to time. And I mentioned also that there's a thing called jerk, and jerk is the third derivative of position with respect to time. Snap is the fourth derivative, and so forth. So we have these things. Well, all those equations we had, the algebra equations, for what goes on with constant acceleration, they pop out of the calculus once you understand integral calculus. Or they sort of pop out once you understand differential calculus. For instance, we know that the change in velocity is equal to the integral from some original time to some final time of acceleration with respect to time. And if that acceleration is constant, then that can come out of the integrand. And we want to be formal about this so that we don't upset the mathematicians. We should use a dummy variable here, call that dt prime. And so we make that integral, do that definite integral, and we get change in velocity is a times t final minus t original. That's a times delta t. That's what we had before. We can do that then with position. So we know that change in position is the time integral of velocity with respect to time. So now we have to reorient this to be a function of some final velocity. So we'll call this velocity at any given time is equal to original velocity plus acceleration times, we'll call that time. We're going to let time 0 be 0 there. So we take that, drop that in here. Delta x integral t0 t final of v0 plus a t prime dt prime. Okay, so the integral, let's give a space. So delta x is the integral t0 t final v naught dt prime plus integral t0 t final a t prime dt prime. And this becomes v naught delta t plus 1/2 a t prime t prime squared evaluated from t final t0 to t final. So v naught delta t plus 1/2 a delta t squared. So understanding the integral and differential relationships between acceleration, velocity, and position and time can get you the algebraic relationships. if you have the function of acceleration with respect to time. And so that if you know the calculus, you don't have to have the algebra part memorized. You're probably going to use the algebra part often enough that you'll have it memorized anyway, but it does pop out. And then once you have that equation and the velocity one we derived earlier, you can play with algebra and get the other two equations also, since there's only two independent ones. That's it.